Hello good day viewers. Into this tutorial we are going to see the electronics. The first part of electronics will be explained in this video. In this tutorial we are going to see the Zener diode, the semiconductors and electronics and its components, and the voltage diode and current diode and rest. If you are first to this channel, kindly consider subscribing so that you will be notified immediately if I uploaded any content. So, focus on this topic that we are going to see. The course itself, its name as what? Electronics. Under electronics, we are going to see various topics. So, the main thing that I'm going to tell you is that whenever I'm writing, kindly share a piece of paper and write each and every definition and formula whenever I write, because this is a video of exam review, so that you will learn more on electronics. As usual, don't forget to subscribe to the channel for more exciting videos. So we are going to talk on electronics. We are going to talk about electronics and components. Electronics and Electronics and components. The course itself is named as Electronics. And the topic under it that we are going to see, we have to know electronics first and its component. So what is electronics? It says that electronics is something that is dealing with the flow of electrons. The definition I have here, it says that electron is a study of flow of electrons in various devices. Let me write the definition here. It says that electronics is the study of So this is the definition of electronics. Electron is the study of the flow of electron in various devices. And also there is a definition that says that electronic is a branch dealing with electron flow and control device. So therefore we have two definitions. This is the first definition that I give. I said electronics is the study of the flow of electrons in various devices, system and materials. And therefore electronics is a branch dealing with electrons flow or control in devices. So this is the definition of electronics. So we have to see the component of electronics. As you all know that we have two components of electronics. We have passive and therefore we have active. The passive elements are elements that don't produce power, and therefore the active elements are elements that produce power. So therefore the passive elements are elements that don't produce power, and therefore the active elements are elements that produce power. So therefore what are passive elements? Passive elements that don't produce power are, we have the resistor. We have the resistor, and therefore we have the capacitor. Capacitor is inside, and therefore we have we have the inductance. We have the inductance, and therefore we have transformer. So first, this is a transformer. This is a flux. This is flux. Let's say this is what we call the primary windings. This is the secondary windings. Let's say this is flux. This is E1. This is E2 for secondary winding. Let's assume this is a transformer. So therefore this resistance, capacitor, this resistance and capacitor also, the inductance and this transformer, they are passive elements. Passive elements are elements that don't produce power. But what of the elements that produce power? It means we are talking about the active element. The active element, we have op amp. Op amp. What is op amp? Op amp, it means the operational amplifier. operational what? Amplifier. The operational amplifier, let me illustrate it. Let's say this is operational amplifier. I'm not good in sketch. But as we all know the operational amplifier. So the next example on the active element, we have what? We have the diode. We have the diode. So therefore, we are going to talk about the diode also in this video. Without wasting of time, let's see as the third example under the active, we have what? We have the LDR resistor. So therefore, this is all for what? Electronics and what? And components. So therefore, let's see some semiconductors. So let's talk about the semiconductors. What are semiconductors? Semiconductors is a conductivity between what? Between conductor and insulator. So first I have conductor. And therefore I have what? Insulator. So therefore semiconductor, yeah, is supposed to have what? Semiconductor. Because I said semiconductor is a conductivity between what? Between conductor and what? An insulator. So on a semiconductor, what shall I going to tell you second? There is what we call the single crystals. It is what we call the single crystals. So what are the single crystals? In the single crystals, I have the two things to tell you. I have the silicon, which is known as Si, and therefore I have what? The germanium. I have silicon and I have what? Germanium. And you have to know that there is what we call the compound crystals. So what are the compound crystals? I have what? I have the gallium arsenide, and therefore I have the indium phosphide. So therefore these two are what? These two are the compound crystals. And therefore you have to know that the gallium arsenide, used for high-speed what? Integrated circuits. The gallium arsenide, it is used for what? For high-speed integrated circuit. So therefore, if we say the gallium arsenide, it is used for, let's say, high-speed integrated circuit. So therefore, what of Si and what? What of the silicon and what? And germanium. Germanium use, it is what? It is temperature sensitive. And why the silicon, it is what? Less sensitive. So therefore under semiconductor, I define what is semiconductor, and therefore I have the single crystals and what? And compound crystal. Whereby in the single crystal I have the silicon, germanium. Compound crystal I have what? The gallium arsenide and I have the indium phosphide, and therefore I said that germanium use is what? It is temperature sensitive, and therefore what? Silicon, it is less. But why the gallium arsenide used for what? Used for high speed integrated circuits. So the next thing I have here is that we're going to move towards semiconductor physics. What are semiconductor, or what properties can we see under the semiconductor physics? So semiconductor physics, we know what is semiconductor. So from your own understanding, what is semiconductor physics? Semiconductor physics is a study of behavior of electrons and hole in a semiconductor materials. So what do we mean by that? We mean that there is something that we call the energy band theory. But before that, Semiconductor, as I said, is a study of what? Of behavior of electrons and what? And what is semiconductor materials, including conductivity, mobility, and what? And recombination. So therefore, we are going to see what is the mobility and what? And conductivity. Let me write the definition of the semiconductor physics. Let's say semiconductor physics is a study of the semiconductor physics. Semiconductor physics is a study of what? Behavior of electrons and hole in a semiconductor materials, including the conductivity, mobility, and what? And recombination. Mind you, don't forget to write anything and any theory that I'm writing in what? In the board. Because it is very important, because whenever you're going to do your exam under electronics, you must be asked to solve this kind of what? To ask, because we're not coming to examples, but we are going to see the formulas, because whenever you know the formulas, you will be able to what? To solve any kind of example. So therefore, this is the definition of semiconductor physics. There is what we call energy band theory. The energy what? Energy band theory. So therefore, under this energy band theory, we have the band gap, we have the balance gap, and we have the forbidden gap. So therefore, we are going to see each and every definition under this. So therefore, itself, energy band theory, what does this mean? It means whenever you come across something called the energy band, forget about the theory, energy band. It means what? It means the ranges. Ranges of what? Ranges of energy. That's all. This is in one word. So, under this energy band theory, there is what we call the valence band. Yes, it is also the first thing that I have here, which is what? The valence band. What is valence band? Valence band is the energy that contains valence electrons, typically fully occupied at low temperature. It means that whenever we hear something about valence band, it means that what? Energy that contain electrons in its what? In its band. It means that it occupies itself in what? At a what? At a low temperature. Yes. So the next thing that I want you to know is that what is conduction band? We have what? Conduction what? Conduction band. But you have to know that the energy band, it says that it is highest occupies electron what? Electron-volt. Highest occupied electron band. So therefore, what is conduction band? Conduction band, you have to know that we said this is the highest. Sorry, this is under valence. This is under valence. Because we said the valence band, it is what? Highest. So therefore, the conduction band, it is what? It is lowest what? Occupied electron what? Electron band. Sorry for my writing. So you see that the difference between the valence band and the conduction band is that the valence band, it is what? It is highest occupied electron band, but why the what? The conduction band, it is lowest what? Lowest electron band. It is lowest what? Okay, sorry, this is lowest unoccupied. Lowest unoccupied electron band. So therefore, the next band we have what? Band gap. There is what we call band gap. This band gap, it is very important because most of the calculation that you do in electronics, you will be hearing something about the EG, which is band gap. So therefore, also in LED light emitting diode, we are coming to it. Its formula, it starts from what? From the EG, which is what? The band gap. So what is band gap? Band gap is energy difference between what? Bands. Suppose this is a band. Suppose this is a valence band, or this is what? Suppose, yes, I have valence band. Let me say I have conduction band. So therefore, the band gap, it is between two what? two bands, because it says that the energy difference between two bands, whatever bond we have in top and down, so therefore the middle of them, it is what? It is this band, what? Band gap. So therefore it's the difference between what? Energy difference between bound. This is that is the definition of what? Of band gap. So what of forbidden gap? Forbidden band, okay, sorry, forbidden band, not band. Forbidden band, same as what? Band gap. They are the same as band gap, but we can define it as is an energy gap between valence and what? And conduction band where electron can exist. As I said, band gap, it is what? It is at the center of two bands, but I did not identify which band. So therefore, the forbidden band is between valence and conduction band. So therefore, this is what? Also, I said band gap is the same thing as what? As forbidden band, because they are at the middle of what? Of band. But the main difference is that, or let me say, it is not a difference, but rather, let's say, a relationship. But I don't know what to call it. But you have to understand this. Band gap is between two bands, but we are not identifying the band that is between them. But in forbidden band, they are given they say that the main difference, it is not a difference, but how can we identify forbidden band? It is between valence band and conduction band, because the first I identify what I define what is valence band, and I define conduction band. So the definition of forbidden band is between valence band and conduction band. So first, this is valence band, and this is what? This is conduction band. So the band that is between them, it is what? It is forbidden band. So this is the definition of forbidden band. But also the definition of band gap, it is the middle. It is in the middle of this. But the band gap is defined as what? Middle of two bands, but we are not identifying which band. I have to get it. So therefore, the next thing we have to do some material classification. Let me clean the board. So here are the word material classification. Sorry, here I have long. So therefore, what is the word? What is the band gap? Band gap of insulator. Band gap of insulator, it is greater than what? 5 electron volts. So what is semiconductor? The band gap semiconductor, which is moderate of this band gap, it is what? It is from 0.1 to 3 electron volts. Yes, from 0.1 to 3 electron volts. So I have to explain what is electron volt, and therefore I will come for it. And therefore the energy, the band gap for what? For conductor, which is the overlapping band, it is what? It is always what? It is 0. So therefore the next thing that I want you to know is that we have to talk about what? Energy units. As I said, I will explain what is electron volt. So therefore, one electron volt, it is equals to 1.6 times 10 to the power of what? Negative 19 what? 19 joules. Take a sheet of paper and write those formulas because they're very important. So what is electron volt? Electron volt gained by what? Electron through 1 volt. It means 1 volt potential. We all know that voltage is what? It's like potential. So therefore, whenever we say that something electron volt, it means that what? It means that it is energy gained by what? By one voltage potential. So therefore, let's have some band gaps table. So here are some band gap tables. The reason why I gave you this is that because in examples or in exam you might be asked for a calculation. They will ask you a calculation, and therefore maybe the calculation it is talking about silicon, and therefore you are looking for the band gap. So therefore the value of the band gap for silicon it is 1.12 electron volt, and for the germanium which is 0.67 electron volt, and for the gallium arsenide which is 1.43, and what for diamond which is 5.48. So let's move to next. Kindly write it down. It is very important. So the next thing we are going to talk is what? We are going to talk about what? Conduction and carriers. Therefore, conduction and carriers, let's take it one by one. What is conduction? Conduction itself, it is a movement of what? Charge carriers. But what is carriers itself? I say what? Movement of charge carriers. So but we are still on carriers. What is carriers? Carriers, it is what? They are electrons and holes that conduct electricity in what? In a semiconductor. Let me write it so that you can see. So therefore, as I said, the conduction is a movement of what? Charge carriers, and therefore we are going to know the definition of carrier itself. As I said, carriers are electrons and holes that move and conduct electricity in a semiconductor. So let's recall the Ohm's law. Ohm's law, V it is equals to what? V it is equals to IR. And the next thing that we are going to recall is the resistance. Resistance, it is equal to the conductivity L over value of what? Over value of what? Over value of the current. So this row stands for what? It is resistivity, and therefore the value of what? Sorry, there is a relations which says that J it is equals to sigma E, and it is equals to 1 over rho of what? E. The sigma it stands for what? It is conductivity. Relation of conductivity, you can be able to make the conductivity and what? And find the conductivity to be the subject of the formula when you are given a question. But I'm just showing the relationship between them. Yeah, I'm showing the relationship. And therefore the J, the value of J, which is what? Which is the current density, is the same thing as 1 over R. The J is what? Is the current density. So therefore the next, which is the value of what? I have the value of E. As you all know, value of E, it is what? It is electric field. And therefore we have the electric field E is the same thing as what? V over L. So therefore here are some what? Are some relations that I have for you. Kindly write it down, because it shows that the value, the V it is equals to IR, the R it is equals to what? The resistivity multiplied by L divided by A, and this J which is equals to what? The current density which is equals to sigma, it is equals to what? Electric field which is equals to 1 over what? 1 over rho, which is what? The resistivity multiplied by the electric field. So therefore it can relate this relate with this and relate with V, it is equals to IR. So let's see the what? Let's see some charge carriers. So charge carriers. In charge carriers, electrons are what? Electrons are negative carriers. Electrons are what? Are negative carriers. Y holes are what? Y holes, which is P, are positive carriers. Are positive carriers. So therefore let me just read the definition for you so that you can write. So are positive carriers electrons, valence, okay, sorry, I said holes are what? Are positive carriers. So therefore there is what we call the intrinsic semiconductor. What are intrinsic semiconductor? Intrinsic semiconductor is a pure semiconductor material without impurities like what? Like pure silicon and what? Germanium. Wrote it down. Intrinsic semiconductor It is what? It is a pure semiconductor materials without impurities like silicon and germanium. So therefore there is a relation that says that N it is equals to P and it is equals to Ni. What does this mean? It means that the N concentration, it is equals to what? P concentration, and therefore it is equals to what? The intrinsic concentration semiconductor. So this is how the relation it is. So therefore the value of Ni, its constant value, it is equals to 5.2 times 10 to the what? 15 T of what? Temperature of 3 divided by 2, and E, yes, e to the negative band gap divided by the NV what? Yes, okay, sorry, divided by the 2 kT, whereby the K it is the Boltzmann equation, which is equal to, okay, sorry, Boltzmann constant 1.38 times 10 to the negative what? Times 10 to negative 23. Yes, negative 23 joule per Kelvin. So therefore, this is all I have for you for what? For charges carriers. So let's see the mobility and conductivity. As I am explaining it step by step. First, what is mobility? Mobility means how easily carriers move in a semiconductor. How what? How I'm not writing it because of what? Because I have to make the video to be short so that we will learn more, because all this we are talking about some definitions, but we are coming to formulas. So therefore mobility means how easily carriers move in a what? In a semiconductor. And therefore, what is conductivity? From the word conductivity, what comes to your mind? Conductivity measures how well a semiconductor conducts electricity. Conductivity, how much a semiconductor conducts electricity. So therefore, we are going to talk about these two, mobility and how conductor conduct electricity, and how a semiconductor conduct electricity, how well a semiconductor conduct electricity. So therefore, we all know that semiconductor, okay, the conductivity, it depends on carrier concentration and what mobility. It is also has a relation, which is sigma, it is equals to Ne what? Ne mu. Ne mu. So what is the value of this sigma? Okay, first, what is the mu? The mu is stand for what? It stands for mobility. And therefore, you have to know that the gallium arsenide, it has more highest of what? More highest of this mu. And therefore, the E stands for what? The E stands for the electron, and therefore the N stands for what? The number of what? Number of concentration of what? Of either a semiconductor. So therefore, the next thing that I want you to know is that let's move to what? Let's move to mobility comparison. Here are the mobility comparison. So for a material, when a material it is what? Germanium, silicon, or gallium arsenide. So therefore it is value which is what? Mu minus the which is what? The N 300 and what? Okay, sorry, 3900 and what? And 1500. And therefore we have what? Okay, sorry, 1500. We have what? 1500, yes. And therefore we have what? 8500 for what? For the gallium arsenide. So therefore take a sheet of paper again and write this mobility comparisons. Okay, let's see the extrinsic semiconductors. What are extrinsic semiconductor? Extrinsic semiconductor is a doped semiconductor with added impurities change conductivity. Semiconductor is a doped. This is doped. Please kindly write it down. Extrinsic semiconductor is a doped semiconductor with added impurities to change conductivity. There are some of the impurities that is added to change conductivity of what, of a material. Whenever we change it, this is what we call what? Extrinsic semiconductor. So therefore there is what we call the doping. So therefore, what is doping? Doping, it means adding of impurities to increase GaAs. We all know what is GaAs, but so therefore adding some impurities to what? To increase the what? GaAs. So therefore we have what? There is a type of what? Extrinsic semiconductor. Under the types of intrinsic semiconductor, there is what we call the p-type and what? N-type. So we all know what is p-type and we know what is what? N-type. So therefore under the p-type there is what we call pentavalent. Pentavalent, and therefore this is we have what? Trivalent. Okay, sorry, this is for pentavalent, it is what? N-type. For trivalent it is p-type, which is what? Tri-type, which is pentavalent, and therefore we have p-type, which is what? Which is trivalent. So therefore here is what? Here is the types of the extrinsic semiconductor. Without wasting of time, let's move towards P-N junction diodes. P-N junction diodes. So therefore this is just quick review of your exam. Whenever you're going to do exam, if you watch this video completely, inshallah you will score the highest and you will pass the course. So therefore the P-N junction formed by joining P and what? N. So by the word P-N, you know that we are going to join P-N type. So we all know this. So there is what we call the variable potential. Variable potential, which is known as what? Diffused voltage. Diffused voltage, which is V0. This is diffused voltage. So therefore, we know that germanium, which is what? 0.3, and therefore the silicon, which is 0.7. As you all know, in the last table that I draw is that we have the band gap of the value of what? The band gap of the value of silicon, which is 1.1. So this is not a band gap, but what? We are talking about the build voltage. So the build voltage for germanium here and silicon, it is what? For the germanium, we have 0.7, and for the silicon, we have what? 0.7. Okay, germanium 0.3 and silicon 0.7. So therefore, you can write it down so that you may use them in some of your examples. So, and for the gallium arsenide, it is 0. Okay, it is what? 1.2 voltage. So the built-in voltage formula, it says that the V0. So now we are going to write the formulas. So therefore you have to, care must be taken, because those formulas will be used in your calculations under our electronics. So therefore the formula says that the VT, which is the terminal voltage into lane of what? ND and what? And NA divided by what? Divided by the value of NI squared. So therefore here, what is terminal voltage? The terminal voltage, which is known as what? Value of what? KT divided by Q. Yes, KT divided by Q. But terminal voltage, this is natural log. This is what? Dono. Number of dono. And this is what? N what? A, which is what? Acceptor. And we all know that the value of Ni, I wrote the value of Ni, the constant, which I say it is what? It is intrinsic concentration of a what? Semiconductor. So therefore, you have to what? You have to square it. So the next thing that I want you to know, you all know that the value of what? K, which is the Boltzmann constant, 1.38 times 10 to the negative what? Times 10 to the negative 23 what? Joule per joule per Kelvin. So therefore the value of charge, the value of Q, which is what? The value of Q, which is 1.6 times 10 to the negative what? 19, which is charge. So therefore, as you can see, this is what? This is built-in voltage. V0, which is equals to the terminal voltage into natural log of ND of NA divided by the value of what? Intrinsic concentration of a semiconductor squared, which I write the formula, I think I said 5.2 something to the T of 2 over 3 into E exponential of what? Exponential of the band gap of what? N something like this. I write the formula, so therefore you can get out to the video. You can see the formula. So therefore the next thing that I want you to know is that for the terminal voltage, because if we are given, if the value of K is this, and the value, so first let's say the value of temperature, it is 300 Kelvin, and when you multiply it with this, and the value of Q, which is this, so therefore our new terminal voltage will be what? Will be 26 millivolts. Yeah. So therefore the next thing that I want you to know is that the bias condition. So what is bias? Bias, it is just a PN junction. What I say bias condition. So therefore bias, it is what? It is a PN junction. So therefore we have the forward bias, and therefore we have the reverse bias. So therefore you have to take note on this bias condition, because it is very important. We have the forward bias. We have the forward what? We have the forward bias. So therefore forward bias, it is what? It is whereby the positive and goes to what? Goes to negative. What I mean is that the P side positive, it's what? It conducts. It means the P side positive what? Conducts. But why the reverse bias, which is what? From what? From negative phi to what? To positive. It means that what? From P side to negative blocks. P side negative blocks. As I said, P side positive, it conducts, and therefore P side negative block is the same thing as saying what? The positive into N in the arrow of this negative. It means from what? From this positive to negative, and from what? From this negative to what? Negative to positive. So therefore, and you have to know that from in reverse bias, only IS flows. IS, it means what? The current. The current, it means that it is only the current that what? That flows. Which means the IS, it means the reverse what? The reverse current. It's only the reverse current flows. So therefore we have to talk about the diode X's. X's, I mean characteristics. So therefore the diode characteristic, there is what we call the Shockley theorem. Shockley equation. So what is Shockley equation? Shockley equation, it says that the direct current, which is equal to the reverse what? The reverse bias, which will be equals to what? The exponential of what? Exponential of BD divided by N of the terminal voltage minus 1. As I said, the formula of terminal voltage, which will be equals to, I think I said KT divided by what? Divided by the value of Q. So this is the value of what? Of the terminal voltage. So therefore there is what? As I said, the IS, it is what I explained before, which is what? Reverse. Which is the reverse bias, which is what?
RS, reverse bias. So the next thing that I want you to know is that there is something we call capacitance effects. Capacitance effects. So the capacitance effects, which is what there is what we call transition what? I think it's transition temperature, but I have to check it. Transition capacitance, yes. Transition capacitance. So therefore this transition capacitance has its own formula, which says that the value of C naught divided by 1 plus the magnitude of what? BR divided by what? Divided by VK magnitude of what? Value of N. So this is the transition capacitance, and this is what? This is the C naught. The C naught stands for what? 0 what? I think 0 capacitance. Which is what? The C naught, which is the capacitance naught, is known as what? 0 bias capacitance. Which is what? 0 bias capacitance. And therefore, this value of R, it is what? Reverse VR, which is what? Which is the reverse voltage. And therefore, the VK stands for what? The knee, which is what? Knee voltage. And what of the value of N? The value of N, it is usually N, it is equals to 1 over 2 or what? Or 1 over 3. So therefore, after capacitance effects, under it we have the transition capacitance, whereby we explain this formula. The next thing that I want you to know is that the diffusion capacitance. The diffusion capacitance, it is whereby we have the minority carriers. You know that we have minority and majority. So therefore, we have what? Diffusion capacitance. Diffusion capacitance. The diffusion capacitance stands for what? CD, which will be equals to what? The minority carriers the minority carriers multiplied by what? Divided by the value of knee voltage multiplied by what? By ID. As you all know, the value of what? Diode current, which I said is equals to IS. IS into bracket of what? Into brackets of, I said, which is the, I think, energy gap divided by N of what? Of VT. Yes, okay, sorry, this is what? This is VD. I said and then minus 1. This is the formula for BD. So therefore, if this question is given to you, the diffusion capacitance, you have to first find the value of ID, and then you have to substitute it here and then multiply this. This is called what? The what? The minority. The minority carriers, and therefore YVK, it is what? It is the new voltage. Minority carriers lifetime. So therefore, the next thing that we want to know here is that, let me talk on diode resistance. Diode resistance. So let me clean the board. So therefore, we are going to talk about the diode resistance. So what are the types of diode resistance? Diode resistance, it have what? It has types. What is diode first? We all know that. Let's say this is sign of diode. Let's say here is a circuit. Let's say we have another diode here. Let's say I have another diode, it is looking up. So let's say, assuming this is a circuit, I have diodes. So therefore, this is diode, this is diode, this is diodes. So therefore, you have to understand, whenever a diode, it is looking what? It is looking up or down. It is what? Its sign, it is changing, either positive or negative, when it is looking forward or backward, or when it is looking upward or downward. So we are going to talk about the diode resistance. So what are the types of diode resistance? Let me put it in table. In table there is what we call DC static, DC or what? DC or static. So therefore there is the types of resistance. We have DC static, which stand for RD, which is equal to what? VD divided by what? ID. The voltage diode divided by the current diode. And therefore the AC, which stands for what? RD, which is equals to what? dVd over what? Over delta. It means delta. That's the reason that we write what? This small v, because we're writing the delta. So therefore divided by what? The current diode. So therefore there is a description that we have here. The description here, it means that what? We have point on what? Point on cup. It means the DC or static diode, it is on what? On a cup. And therefore the what? The AC or dynamic diode resistance, it is on what? It is slope on a point. Slope on what? Let me check. Yes, slope at what? Slope at point Q. It means that this slope at point Q, the DC operating point. It is a DC what? Operating point. So therefore there is what we call the equivalent circuit. What is equivalent circuit? Equivalent circuit, as we all know, it is, let's say we have equivalent resistors. So therefore this is called equivalent circuit. Equivalent of circuit, it means the equivalent of whole circuit, the piecewise and the knee and rest. So therefore let's see what formulas can we get. We have the piecewise. The piecewise, which will be equals to the VD. The diode voltage, it is equals to VK, which is the knee voltage, plus what? Plus I what? Plus ID, R average. The R average, it is meant that we are going to find what? Suppose we are going to find the equivalent what? The equivalent circuit. So therefore let's say this is VD, it is equals to what? VK plus what? Plus ID, R average, if I divide both sides by the value of what? Vk. Or let me say, before dividing both sides, whenever the value of k comes across, it will become what? Vd minus what? Minus Vk. It is equals to what? Id, R average, divide both sides by what? By Id, divide both sides by Id. Id will cancel Id, so therefore the R average, which is what? Vd minus what? Minus Vk, divided by Id. Yes, this is what I have here. So therefore there is what we call the simplified. I have you write this. Kindly pause the video and copy this. So therefore there is what we call the simplified. The simplified, which is equals to VD. VD, it is equals to what? VK into what? Ideal diode plus knee voltage. So therefore there is an ideal also. Ideal, which is VD, but it is always 0 when it is on. So therefore the ideal, which is equals to the VD, it is equals to 0 when it's what? When it's on. So therefore there is something that I want to tell you, which is what called, we talk about diodes. So therefore we are going to talk about what? The Zener diode. So what is Zener diode? Zener diode designed to operate in reverse breakdown region. So therefore, as you all know, Zener diode, it is also what? A reverse. So it has its own properties. The definition: Zener diode designed to operate in a reverse breakdown region. So its properties, it means it operates reverse breakdown, and therefore the VZ voltage, sharp breakdown voltage. But let me write it on the board. So therefore, this is the properties of Zener diode. As I say, the definition of Zener diode, designed to operate in reverse breakdown. So its properties operate in reverse breakdown, and the VZ, Zener voltage. The VZ stands for the Zener voltage, which is what sharp breakdown voltage. The Zener current, which is IZ, reverse current breakdown. So we have the TC, which is the terminal coefficient. It means this is the subject of the formula. So therefore, the TC, the temperature coefficient, it has its own formula, which says that, I think it is delta VZ. Okay, let me check. Yes, it is delta VZ divided by what? Divided by VZ, all divided by what? T1 minus T0 multiplied by either percentage or what? Or degrees Celsius. Degrees Celsius. It means that when you are given percentage, you are going to multiply it by that percentage. But if you are given degrees Celsius, so rather you are going to multiply by what? By degrees Celsius. So I think that, okay, the value of T1, it is what? Okay, sorry. What is T1? T1, it means the what? The junction temperature. But why T0 is called what? The ambient. The ambient temperature. Yes, it's right. The ambient temperature. So after then, there is what we call the what? Voltage regulator design. Let's see the voltage regulator design. Kindly write this down. Let's say we have voltage regulator design. So also voltage regulator design has its own formula. So the voltage regulator design, R, it is equals to what? The VI minus VZ divided by what? Divided by the IZ minus what? IL. So the value of VI, which is the same thing as what? The voltage input, and therefore the value of BZ, the Zener voltage, and the IZ, which is what? The currents, what? The Zener current, and therefore the value of IL, which is what? The load current. So therefore, there is something that I want you to know. The value of PZ. What if I say the value of PZ? As we all know that, which means the dissipated power. We all know that power, it is equals to IB. So therefore, if I am asked to find the BZ, it's the same thing as saying the IZ multiplied by what? BZ. So therefore, it will give me what? The PZ, which is what? Power what? Power dissipated. So let me check over there. We have some formulas. So there is what we call the on and off. There is on or off condition. So how can you identify whether a condition it is on? So when condition it is on, the V, it is what? It is greater than or equals to value of what? Of Zener voltage, which implies that B0, it is equals to VZ. Whenever V, it is greater than or equals to VZ, that condition it is on, so therefore B0 is equals to VZ. But when that condition it is off, it says that V it is less than the value of what? VZ. This implies the V0, it is the same thing as what? Value of V, not VZ. So the next thing I have here is design what? There is something that we call the design cases. So all these formulas are more important because you might need them in calculation of what? Under electronics, the first part. This is the first part of electronics. The second part, I think it is talking about the power supply and what? And rest. So therefore we have what? We have design. Yes, design cases. So the design cases, we have fixed system. Fixed system is like the values that we have in our variables. Because suppose the variable is given, maybe the variable is like the subject of the formula. There is what we call the fixed variable. The fixed variable, we have the v what? Yes, we have the v in, which is minimum, and therefore we have the RL also, which is what? Minimum. So therefore, what of the fixed system? Fixed system, we have the value of Vi, which is the input voltage, and therefore we have the resistance, and therefore we have the RL. Are what? All are fixed. But we have Vi minimum, RL minimum. So therefore, let's see each and every of the formula. So therefore, I am going to start with Vi minimum. So what will be its formula? Its formula says that the value of RL plus what? R multiplied by what? Multiplied by Vz divided by what? Divide by the RL. So what are the formula of this RL minimum? It says that the value of what? RVL, R multiplied by VL divided by what? The input voltage minus what? Minus the Zener voltage. So therefore, this is all I have for you for some of the formulas. But let's move to LED, which is called light emitting diode. LED means what? Light emitting diode. So what is light emitting diode? In practical, let me say that there is a globe that you'll be seeing inside a charger like this. You see the terminals. The long one is the positive terminal, the short one is the negative terminal. So therefore, these are called LED. So therefore, the relation, as I said before, relation of LED, you might be ending with what? The band gap, which is EG, which is equals to what? HC, and therefore, this is equals to HC. The H stands for what? Planck's constant. Planck's constant, and therefore the C is what? Is the speed of what? Of light. So therefore, in the LED, which is equal to, okay, sorry, this is not C, this is F, and therefore the band gap, which is equals to F, which is the frequency, and therefore it is the same thing as equals to HC divided by the value of what? Value of this lambda. So therefore, wherever this is what we call what? The speed of light. Speed of light. So therefore, what is the value of the speed of light? Speed of light, as we all know, it is 3 times 10 to the power of 8 meters per second. What of the Planck's constant? Planck's constant, I think 6.65. Okay, 6.626 times 10 to the negative 36 joule second. And this is what? Meter per second. So this is the relation on what? On the light emitting what? Light emitting diodes. So therefore, I have some color on what? Materials and their typical voltage. So let me see them. So here are some value of color with their materials and their typical voltage. Red, green, blue, white with their material, gallium nitride, gallium phosphide, and rest. It has their values, which is the typical voltage of each and every color, and it is material. So there is one thing that I want you to tell you. There is what we call the series resistance. Let's say series resistor, not resistance, sorry. So the series resistor, it has its formula, which says that the RS, which is series resistor, is something and VI minus what? Minus VD divided by the value of what? IF. So we have different formula in this course. This course, it is very easy, but the main idea is to what? Is to cram and know all formulas and what? And relations. And the next thing that I'm going to, I have the application of LED. Application of LED. let me say application. So the main application of LED is I have this, let's say this. This arrows, this dash that I'm seeing there, what we call the segments. So therefore in LED, these are the 7 segments from what? They are what? They are 7 segments from what? From 0 to 9. In any counting numbers, either the stopwatch for showing numbers, and like the traffic lights and the rest. So it is using this LED. This LED, whenever the LED, I'm going to get 0 because it is just a connection, and it is a connection here, connection. Whenever I remove the connection in this, I will end up with 0. So therefore, I remove one connection over here, it gives me 0. And therefore, whenever I need 1, I'm going to delete this and delete this. It means I'm going to reconnect it, man. What I mean is that the connection, I'm going to remove it. Let's say this is on, this is on, let's say this is what? This is off. I on it. Whenever I on it, it will become this. Whenever I off it, if I on it, it is the same thing as like this. Yes, as like this. But whenever I turn it off, I turn this off, I will come with getting 1. So therefore, whenever I need 7, I'm going to connect this, and I will disconnect this, disconnect this. So here are the 7 what? 7 segments. 7 segments. 1, 2, 3, 4, 5, 6, 7. So here are the 7 segments. It is this 7 segment give us the digits from what? From 0 to 9. So there is something that I want you to know, which is called the photodiode. What is photodiode? Photodiode operate in reverse bias, generate current when light hits PN dark currents. So therefore you have to write this. Photodiodes operate in reverse bias, generate current when light hit. It means that it is generating current when light it is hit the PN what? The PN junction dark current. The PN what? The PN junction of dark current. So what is that dark current? Dark current, it is IR. So the value of IR current, which is mean, when we say dark current, we mean that there is no light. It means no light. So therefore, its formula says that IR, which is equals to what? Which is equals to M, which is electric what? The electric field. And therefore, the M stands for what? The M stands for sensitivity, which is mean in slough. But this is what the IR is in what? Linear. Is in linear. And therefore, reverse. Okay, sorry. The dark, I said dark resistance. Yes, dark resistance. The dark resistance, which is R and R, it has the formula. Let me write it here. R and R, it has the formula of what? VR over IR. Don't forget the Ohm's law. The reason why I write the relation between the resistance, the conductivity and what? And the Ohm's law, it means that you all know that this is Ohm's law. If I cross multiply, I will have V, it is equals to what? IR. As I said before, if I'm looking for the power is equals to IV. So I will say the power zina, it is equals to me the current zina diode and what multiplied by V zina. So this is not much harder, but just concentrate and recall what you have been done in the last fast. So therefore, the dark current, we have dark current and we have dark resistance. So this is what we call what? The dark resistance. And this is called what? Dark what? Okay, this is dark current. Sorry for the mistake. This is dark current. And this is what? This is dark resistance. This is dark current and this is dark resistance. So make sure you write it down. The next thing, it is what? The last but not the least, it's load line analysis. Load line analysis, there is something that we call KVL. Load line analysis, there is something that we call the KVL equation. KVL equation. So what does KVL equation? The KVL equation, it says that the E, it is equals to what? The VD, the diode voltage, plus the ID multiplied by the resistance. So this is what? This is the KVL equation. And therefore there is the KVL equation under what? Under the load line analysis. And there is what we call the intercepts. They are the intercepts. The intercept is showing that in X intercept, we have to know that the ID, it is equal to what? It is equal to 0. When what? When the diode voltage, it is equals to E. But why intercept? Why intercept? Which means this, we are talking about what? The ID, which is the diode current. So here we are talking about the voltage diode. The voltage diode, it is equals to 0 when the value of what? ID, it is equals to V. Okay, sorry, it is equals to E over R. The E is the same thing as voltage, but here we are referring to what? We are referring to what? We are referring to R, which is okay. We are referring to E. So intercept, X intercept ID, the current diode, it is equals to 0 when VD, it is the same thing as what? As the voltage, which is what? Which is E. And therefore the ID, which is the current diode, is the same thing as, okay, in the Y intercept, VD is equals to 0, but when ID, it is equals to E over R. So here, colleagues, my dear colleagues and the rest of the students, this is all I have for you for electronics quick exam review. Please kindly consider subscribing to my YouTube channel for more exciting videos. Don't forget to like and comment. This video, it is just, I can't say an introduction, but it is also for beginners, an introduction to electronics, and whether you are at the minute of entering exam in less than 30 minutes, you can watch the complete video. It will make sense when you enter the exam hall. Don't forget to subscribe to my YouTube channel, and I hope this video will help you. And don't forget to write those formulas. Guys, write those formulas, are very important, and some of the definitions. I hope this video only might lead you to pass your exam, inshallah, by the grace of God. Don't forget to subscribe, like, and comment. Thanks you for watching. Have a nice day.